This video is picking up after the neuromuscular junction video. As you can see on the left-hand side of your screen, you can see a little bit of the axon terminal, the synaptic cleft, and that's where you had the neuromuscular junction being formed. What this video is focusing on is the generation and propagation of an action potential. Now, this particular process, the generation and propagation of an action potential, will occur both in the muscular system as well as the nervous system. Same process in both systems. So let's start off with the idea of the resting membrane potential. Now, for the resting membrane potential, the inside of the membrane is going to have negative charges. For the muscular system, this is going to be a negative 70 millivolt resting membrane potential inside of the membrane. So what I'm doing is showing you kind of symbolically the inside's negative, the outside's positive at rest. With the resting membrane potential in place now, we can look at where the signal is coming from. This particular instance is using the neuromuscular junction as a way of trying to reach threshold. We can remember that we had sodium coming into the cell. So we have these positive sodium ions coming in. We can also remember we had potassium leaving the cell. Now hopefully remember that there was more sodium than potassium, which is creating a graded potential. So as the sodium entered the cell and potassium left the cell, that's going to cause a change in the localized membrane potential. Ultimately, if threshold is met, we're looking to cause a stimulus. We're causing a stimulus to open a voltage-regulated sodium channel. So this voltage-regulated sodium channel is going to allow for a lot of sodium to rush in very quickly. What that does is it brings all of these positive ions flowing very quickly into the cell. Now the positive ions going in are going to cause a change in the localized membrane potential. The inside is becoming positive, while the outside is becoming negative. So what we've done with this one single voltage-regulated sodium channel is cause that particular point to depolarize. So again, the threshold was met by the graded potential from the neuromuscular junction. Once that threshold was met, it was able to then open the voltage-regulated sodium channel. That allowed the sodium to rush in. So we've now changed the membrane potential or depolarized at that one particular point. The question now is, what happens to all this sodium? All this sodium, it's moving down what's called an electrochemical gradient. It's going to move from a high concentration down to a low concentration, because right where this overall influx is, the high concentration, that's going to move to a lower concentration ahead. So it's going to start moving forward. But it's also moving down from its positive environment to its negative environment. So right now where it came into the cell here, it's mostly positive. But up ahead, the membrane potential is still mostly negative. So as it moves down its electrochemical gradient, it's going to cause the next voltage-regulated sodium channel to open. That voltage-regulated sodium channel is going to open up. It's going to allow for an influx of sodium. So we've now created an increase in sodium concentration again, which means that the membrane potential is also changing. The inside is now becoming positive. The outside is negative at that point. So what happens? You again go down the electrochemical gradient, and that movement down the electrochemical gradient causes the next voltage regulated sodium channel to open. This means that we have another influx of sodium rushing into the cell. And it will keep going down the membrane in that fashion. What this is doing is creating a wave of depolarization. All these sodium ions keep moving down the membrane and triggering the next voltage regulated sodium channel. But that's only half the story. We have to reset or get back to the resting membrane state. So what happens is, we're going to have, as these sodium ions move along, so remember, these sodium ions have all moved down, they've gone down the electrochemical gradient. So once this signal has left, the voltage regulated sodium channel is going to close. That'll prevent any further sodium from coming in. But what will happen at the same time is you're going to have now a voltage regulated potassium channel opening. This voltage regulated potassium channel is going to allow potassium to flow out. So we're taking all of these positive ions out of the cell now. That means that the membrane potential is now changing again. Instead, what's happening is the outside is going positive again, and the inside is going back to negative. We're repolarizing the cell. And that will keep occurring. As the sodium moves down the membrane, down its gradient, you lose the higher concentrations, and that allows the end of depolarization to occur. That end of depolarization is because you have the concentration gradient of sodium decreasing. As more sodium moved in the cell, the high to low concentration has been reduced. Also, because of all the sodium now in the cell, you have a positive environment locally inside. The positive sodium ions don't want to travel into a positive environment. All of this together ends depolarization. And as depolarization ends, we're able to close the sodium channels. This will allow us then to open the next voltage regulated potassium channel. So as that voltage regulating potassium channel opens now, the potassium ions are exiting the cell. As they exit the cell, that's taking the positive charge out and allowing for the change in membrane potential. The inside's negative, the outside's positive. This is repolarization. So overall, what we're looking at here is a wave in the ocean. Think about the front portion of a wave, the very front side. That is the voltage regulated sodium channels opening. As that wave, that front part of the wave passes beyond a certain point, then the voltage regulated potassium channels open. What's happening is every time the ions are moving, one channel is opening, then the next channel opens. It's creating a wave movement down the membrane. I've now added a graph into this image to try and give some perspective to the overall process of an action potential. You'll notice that up on the graph, there's the at-rest point. That's the resting membrane potential. So for example, this area right here is your resting membrane potential. The inside is negative, the outside is positive in relation to each other. You then get this stimulus being applied. So you can notice it's going from the negative 70 millivolts up to negative 55 millivolts. That's what's occurring right here. So that slight increase right here is when you have the chemically gated channels opened and the graded potentials are increasing. Those graded potentials are trying to reach threshold. If they do reach threshold, so again, threshold is right here, negative 55 millivolts. If they reach threshold, the voltage regulated sodium channels will open. That's right here. And that's when you have this voltage rising. That's the depolarization of the membrane occurring. So you have the opening of the voltage regulated sodium channels. Then you're going to have the voltage falling. That is going to be the repolarization. So that's occurring right here. The voltage regulated potassium channels open, allowing potassium to leave the cell, and that allows the repolarization, or the falling of the voltage. Then you have this little drop below resting. It's marked as number 5, the end of the action potential, sometimes known as hyperpolarization. Everything will eventually level out, and you get the return to rest. So really, if we follow the whole process through, the initial at rest, right here, is when things are just maintaining. Nothing much is changing. The stimulus applied right there is going to be now when you have the chemically gated channels open and you have the graded potentials occurring. If threshold is met, we get to have the full depolarization going up. It's at the top of the chart right here that you'll have the voltage regulated sodium channels start to close and the voltage regulated potassium channels open. When those voltage regulated potassium channels open, then you get your repolarization coming down. When you get to the bottom there, the voltage regulated potassium channels are closing. You rebalance and return to rest. So overall, a single action potential will move down the membrane like a wave. You can have several action potentials occurring one after another as long as the membranes are able to reset.